All right, so let's go ahead and get started. It's week 6, and I'll just touch on the syllabus here a little bit. So today we're going to wrap up Chapter 6, which is heat to motive power. So here we are in week 6. I'm going to launch exam 3 this afternoon. I think it'll actually be launched here as we're wrapping up lectures, so go ahead and take that. You've got 2 shots at it. I believe the first 2 exams have been graded already. If something's a little fishy with those grades, let me know. If there's something you felt you got correct that perhaps wasn't graded to your satisfaction, let us know. We can take care of that. And then, I've had a few students asking, hey, I just submitted summary 1 only to the discussion board, and I forgot to put it, in the Dropbox, that's fine. Just go ahead and get those summaries in. I'll grade them. I usually just do a big grading on Sunday night or Monday before Tuesday class. So don't panic. Just get those next 2 summaries in, and I'll grade them. And then we'll also dig into problem set 1 next week. So the semester rolls on. We'll be about halfway done by this time next week.
Wow.
Yeah, really.
Where's it all gone?
It seemed to just really accelerate somehow this time of year. Anyway. Okay, so let's just kind of pick up where we left off last time. We were going through some of the movers and shakers, if you will, of the 19th century England, just as the Industrial Revolution was taking off. There's Threvthik again, and this would be a good Jeopardy quiz. Who named this famous scientist?
Right. Keep all the gray hairs separated.
Yeah, this one's Stevenson, and again, he was the steam locomotive guy who was moving fish back and forth, back in the day. Okay, and then we also looked at some of the very early steam engines. We talked a little bit about reciprocating engines, and now we're going to start talking about turbines. So 6.5 are steam turbines, and I'm just going to pop forward a few more files. Here's a very early example of a turbine, and if we look closely, we can see that the blades here. So this is the turbine without the outer casing on. So the outer casing's been removed. You can see the bolts are still here, so you can imagine the top piece being bolted on. If you look closely, you can see that this side has relatively shallow blades. They're shorter, and here they're cut a little bit deeper. And let's just go over sort of some of the mechanics of how this works.
Why? Yeah.
And then we'll look at these this figure too. So first, let's just back up even a little bit more and look at the ideal gas law. So here's PV equals nRT. And a few things I want to mention about this are that this is pressure, and pressure is going to be measured in PSI. It'll also be measured in pascals, and so you can have or kilopascals or megapascals. The units of pressure are newtons per square meter in SI units. And I'm going to come back and dig a little bit more into what pressure is here in a second. This is volume. And of course, the N is just the number of and there's a lot of different ways to say it, number of particles, molecules, atoms, etc. There are different ways to measure it, or sometimes just in moles is another way. And you're just counting up how much matter is there. This is the ideal gas law constant, and this is temperature. Okay, so in this case, there's five different variables here, and to some extent they're all independent. The R is there just to keep the units straight, but you can imagine. I'll just give you a few little pictures so you can imagine what these are. So you can have, here's your volume, just a box of space. I've drawn it as a box, but you could also imagine it as a cylinder, sort of a tube of air, and that's really what we're doing if we're running a turbine. You could also have a volume inside here. There's also a certain number. I'm just going to draw little dots, sort of count up the number of particles. That's the letter N there. And then what we can do with it, we can squish it. We can push on it from all sides. We talked a little bit about doing that with pistons. That's your pressure. And then we could also heat it. Here's fire underneath, and that's how you can raise the temperature. So there's all different things. We can squish it, which will decrease the volume. We can expand it, which will decrease the pressure, increase the volume. Heat it, which is going to basically put more energy in. So what I want to impress upon you is that this equation is actually an energy equation. And I'll show you exactly what I mean by that. So another good skill to have in engineering or science is to go back and do what's called a units analysis or a dimensional analysis. And whenever you see the word analysis, that just means you're breaking something apart. It's the opposite of synthesis. So synthesis, you're putting it together. Analysis, we're taking it apart. So we're going to take apart that equation. So if we look at, let's just first of all look at volume. It's pretty simple. Volume is measured. So we'll do units first. So here's units. Is cubic meters. And I'm just going to use SI. You could do it in cubic inches if you wanted. The dimensions are just length cubed, right? So meters measure length, and so the units of volume are meters cubed, and the dimension is length cubed. Now let's look at pressure next. P, and I'm trying to draw that as a lowercase p. And I just told you a second ago that it's Pascals, measured in Pascals, which are also newtons per square meter. And if we break down newtons even further, Newton is a kilogram times a meter over a second squared. So the dimensions on pressure are a little more complicated. That's the Newton, and then we divide by meters squared again. So the dimensions on pressure, let's see if we can do this here. Here's mass over time squared And then, let's see, we need length in here as well. Yeah, and I think we end up with just, so we've got kilograms become M for mass, the 2 meters become L for distance, and then the T squared, the second squared becomes T squared for time. I believe that those are the dimensions for pressure. Now, what happens when we multiply volume times pressure? Let's see what happens. So pressure times volume, and we'll just do the dimensions. So we've got mass over length over time squared times length cubed equals mass length squared over time squared. Now, if you remember back to the first lectures when we were looking at the different forms of energy, kinetic energy was 1/2 mv squared. So right off the bat, you can say, look at that. Pressure times volume has the same dimensions as energy. Pretty cool. So now getting back to this figure, I told you that this is an energy equation, and we just proved that or demonstrated that through dimensional analysis, that pressure times volume has the same dimensions as energy. So when you look at this little box of air, or this tube of air and gas, you can see that the harder I push on it, the more energy I'm putting in. So that's really all it comes down to. So it's still mechanical energy. You know, it's not necessarily, it's not, well, the funny thing is it's somewhere between kinetic and potential energy. It's really either or, because the reason I say that is you can see that now temperature itself, if we isolate temperature, I'm going to leave the R out, temperature just equals pressure times volume over the number of particles. So fundamentally, temperature is just energy per particle. And well, what's that mean? It just means that as I squish this box, the particles inside get more elastic energy. They're sort of pushing back with the same force that you're pushing on them. It's kind of back to Newton's laws. Every reaction is an equal and opposite reaction. If you push on the molecules, they're going to push back. They don't want to be squished down into a black hole, for example, right? So they're going to push back. Another way to put energy in is to heat it, and that just means as you're heating it, the molecules are moving faster. Yeah. Each one has more. So that's why it's not exactly potential, it's not exactly kinetic, because down at the molecular scale, you've got these molecules, pushing back like little springs. Mm-hmm. Okay. And you also have them flying around like little billiard balls.
So once you add the fire to it,
yeah,
it's making it looser, kind of. So does that mean that the pressure can increase?
Well, I'm not sure. You're actually
Does that make sense?
Think of it more this way. You're adding if you add the fire to it, it's a little bit more like think of a bunch of cars driving around, NASCAR, Indy 500. As the cars move faster, they're still occupying that same racetrack going around. So I don't know if you want to say they're looser or tighter. They're just more energetic, and when they crash, that energy goes somewhere. So just think of it, you're adding the fire, you're just causing more molecular crashes. Okay. The molecules are just crashing into each other more frequently.
That wouldn't help it to would the heat help compact it? Since the particles are moving faster?
No, it doesn't help compact it. What it does, though, it allows it to expand. And that's exactly, so that's a good little segue. So as we heat that gas on this side, they're moving faster, and they're like, hey, I'm getting out of this traffic jam, I'm going to head down the turbine and spin it. So that's what's going on with the heat.
Okay.
Yeah.
Okay.
So again, it all, since this chapter is heat to motive, I mean, here's your heat at the bottom, and we've discussed the fact that heat is energy, temperature. Again, we just define temperature as energy per particle. Energy per particle, that's what gives us the motive power. So up till now, we've been talking about pistons. Now let's take a look at what's going on in the turbine. And also, what I'm about to say next is the question that for some reason people get confused on and tripped up on the exam all the time, so I'm going to say it now, and this will determine who listened to lecture or not. But here's the dimensions or the axes for a turbine. So up to now in your courses, you've probably been doing a lot of this kind of stuff. You've had the x-axis, the y-axis, and the z-axis. Those are sort of the Cartesian coordinates. They are mutually perpendicular. X is perpendicular to both y and z. Z is perpendicular to both. So all mutually perpendicular. And we can draw that in like so. Now in the turbine, it's a little more interesting. We've got what's called the radial direction. The radial direction is parallel to the axis of rotation. We have the, I'm sorry. I don't know why I just wrote that. Got a little ahead of myself. Sorry, that's the axial direction. Let's see if I was listening to my own lecture or not. This is the axial direction. The radial direction is right here. Radial. So just think of it as along one of the radii of the turbine or the cylinder. And then you have the this other one, and I'm going to draw it here. This is the tangential or circumferential. I think one reason this ends up being a tricky exam problem is that the word circumferential gets misspelled. But now the point is axial, radial, circumferential. So typically axial is labeled as Z, radial is labeled as R, and the circumferential, there's a few different ways. Sometimes that's just labeled as theta for an angle. And you might at first glance say, well, gosh, how are these axes mutually perpendicular? Well, it's pretty easy to see right here that this radius is perpendicular to the axis. If you come out here, so again, well, what direction is the radial direction? Well, it's all of these directions. It's pointing away from that axis. And if you look closely right here, you can see, oh, look, there is another right angle. And I can draw infinitely many right angles around that circumference. So again, the axial, radial, and circumferential directions take care of all three directions. So that's the difference. And there's also spherical coordinates, there are elliptical coordinates, but as long as you've sort of covered all of space, you're fine. You can make up your own set of coordinates. And so that's getting back to what's going on. So along this axis, that's the axial direction. The radial points from the center out, and then the circumferential is just sort of right here, tangent to that. Okay.
So why is the grooves?
Why are the grooves bigger here?
Yeah.
The grooves are bigger here so that the gas can escape. So it's really what you're doing. Think of it like this.
Because if it's a closed system, then where's the gas release?
Well, it's not, what we're probably not seeing here is the exhaust port, yeah, I mean, it's got to go out.
Okay.
Yeah, it has to. Think of it this way.
Sorry, I don't know if that was a weird question.
No, not at all. But think of it this way. Let's just say and this is a kind of an easy analogy to make. You can say instead of molecules inside a vessel, let's just say we just have people. There's everyone's like head from above standing in a room, and we want to get out really quickly. Fire, smoke, whatever, you have to get out quickly. So a couple of different ways to do that. One would be to have a long, narrow hallway. Problem there is, you get backed up. You get backed up in it, right? So danger. Don't go there. Let me see if I can do this. Copy paste. Let's see if I can just grab this, put it over here. Instead, you might say, "Oh, I think I've got a better idea. Let's do this instead. Let's make it shaped this way, and now you can see that everyone can sort of run away faster. They're just more paths.
Okay.
They're more paths for the thing to take, and that's exactly how these turbines work. It just allows the flow to preferentially happen in that direction.
The same applies for entry as well.
Well, like
Yeah, I guess for entry, yeah, if you want to reverse it. I mean, but you take this funnel and turn it the other direction. So everyone, take your seats and go sit in the middle of the row instead of taking the aisle seat right off the bat.
Right.
Yeah.
Well, yeah.
But that's we can even go all the way back to that very first little steam gadget. There's just more spaces for those particles to go. So that's
Okay.
they're
So
gonna
the end of the grooves is just like the release at the end.
yeah they're just gonna take the path of least resistance. But look, we wouldn't put this thing in the way, and yeah the steam is gonna smack that, but ultimately it's just gonna kind of diffuse out into the rest of the room.
Gotcha. Thank you.
Yeah. All right. Okay. So now let's look at this. This is an actual jet engine. So in a jet engine, you have combustion gases going into the engine. So you've got atmospheric oxygen coming in. You have some kind of hydrocarbon going in. When those burn or combust, the resulting molecules, it's kind of like atomic popcorn. You put the popcorn kernels into the popper, put a little heat on it, and all of a sudden, the volume went up. That's exactly what's going on in combustion. You add the oxygen, you add the hydrocarbons, out comes the steam, out comes the CO2, and away we go. There's your jet engine.
Chemtrails.
What's that?
Chemtrails.
Yeah. Those are chemtrails. Yeah, they are. I love that. Now, so let's look at this axis though. So this is the input pressure in megapascals, and let's just get a handle for what that is. So I already mentioned the fact that pressure is measured in pascals, and just like with any good SI unit, we can throw a K on it and get kilopascals, or an M and get megapascals. It's worth noting that 1 atmosphere equals about, I'm just going to round it, it's more like 101, but 100 kilopascals, kPa, equals about 0.1 MPa. So 1 atmosphere is 100,000 pascals, or 1/10 of 1 million pascals. And I should have done a little bit better job, but this K is always lowercase, and this M is always uppercase. And it's also worth noting the P in Pascals is also uppercase, but if I'm going to write the word Pascals, I'm going to write it in lowercase. So all units, when they're written out, are all lowercase. Same as all elements. You know, when you write the elements out, they're lowercase, but then when you abbreviate them, they're uppercase. So just keep that in mind, especially in your writing. So back to this figure. So this is 10 atmospheres of pressure, 20 atmospheres, 30, 40, 50 atmospheres. So basically 5 times what atmospheric pressure is. And we can see that as the pressure goes up, the jet becomes more efficient. So it's not Carnot's law like we looked at last time, where the efficiency was the change in temperatures. These are not Carnot engines. There's no cycle. You know, the gases are not cycling back. They're just like in and then just
Going out.
shooting out. And so the efficiencies typically go up as the pressures go up, and then the jet goes faster. Pretty simple. Rocket science, right there. Okay. So, and obviously, this is for it could be for a stationary, but in general, the jet is moving. So, we're looking at 1,200 meters per second, on the order of 500 miles per hour there. Okay. So here are some of the. So this is an example of a stationary, more advanced stationary turbine. So you have the rotor, which is actually spinning. It's attached to the shaft. Here's the casing and a little bit of a cutaway. Now, as the gases come through, they're basically just playing molecular pinball through this guy. There are also a set of stationary. So these are the fixed blades, the guide vanes, and then the moving vanes. So if we see each one of these vanes, these blue guys right here has a leading edge. Kind of looks like a miniature airplane wing with an angle of attack. And so as those molecules come through in the axial direction, the moving blades spin obviously in the circumferential direction. The fixed vanes then say, hey, change course. I know you were happy sort of moving that way, but keep, here comes another round of vanes, so the stationary sort of kick them back straight so that energy can then become rotational again. So, and with each step, the gas expands, so these sort of get bigger and bigger as you move through the technology. And there's a lot of physics that goes into designing these things. Huge computational, numerical, dynamic simulations. I was not doing this work myself, but there was some really very talented mechanical engineers there at the University of Michigan that were looking at creep. So in mechanical engineering, any material that's stretching. So you can imagine as this blade is spinning, spin your arm in a circle, all the blood rushes out to the end of your hand. Same thing going on here. It's a merry-go-round doing several thousand RPMs. The engine, literally wants to tear itself apart. Those blades want to go flying out through that outer casing. But on the other hand, you want to keep those tolerances tight. So they're looking at creep mechanisms, and creep just means over time the stretch becomes permanent. And if you spin it too fast, it'll fly apart. If you heat it up too much, it'll fly apart, and you end up with boom, failure. end up with one of those numbers. Not good. So anyway, a tremendous amount of material science, thermodynamics goes into designing these engines. Okay, so here's a turbine-powered boat. The captain there is looking pretty fly. All of these things end up with some kind of strange ending. So I'm going to do a little reading in here. It says, how efficient was this new form of steam engine? One answer comes from the basic principles discussed in figure 6.3. I'm just reading now from the bottom of page 198. Assume that the input temperature is the boiling point of water under the pressure of 0.66 megapascals. I'll just write that up. So then we'll get into that figure. So 0.66 MPa is the pressure in. So water and at this pressure, water boils at 163 degrees Celsius. You've sort of squished it, so you have to put more energy in it for it to turn to steam. Kind of the issue that we face here in the Rockies in reverse, where we have less atmospheric pressure, so water will boil at a lower temperature, so it takes longer to cook. So pressure in at 0.66, then the departing steam comes out. So the departing steam comes out at 0.1 MPa and 100 degrees Celsius. So, and those are given in Kelvin. So as it turns out, with this, since this is a heat engine, I might have misspoken earlier. We can actually apply Carnot's formula to it and just say that we're looking at 436 Kelvin minus 373 kelvins. That's that number. That's that number divided by the 436, and that yields an efficiency of about 14.5%. So that's in line with this figure we were looking at previously. So kind of on the lower end, because the pressures are fairly modest, down below 1 megapascal. Okay, so here's the steam engine, and let's see here. It says no actual heat engine achieves its nominal Carnot efficiency, and it seems unlikely that this first engine, that's the one, the previous one, the brass-looking thing, that's first ever achieved an efficiency of even 5%. So very low. Nevertheless, Parsons continued to develop the new machine, and within 5 years, several hundred were in operation. Although wider recognition in other countries took longer, it's an indication both the acceptance of steam turbines for electricity generation, which we enjoy all the time, and that's what's spinning at Colstrip right now, stationary steam turbines, and their rapidly increasing size. In 1898, Parsons and Company invited to supply a 1 megawatt turbine. Pretty beefy for the time, kind of modest for now. Colstrip has 4 turbines. The 2 larger ones are running at 600 megawatts. 600 megawatts, yeah, and the 2 smaller ones are somewhere between 2 and 3 for a total 2.2 gigawatts coming out of Colstrip. Okay, so I want to keep going and talk about this figure. The higher rotational speeds meant that the steam turbine never became a serious option as a propulsive system for road vehicles, nor did it replace the reciprocating steam engine for locomotives. It did, however, find one major application, a marine engine. Parsons foresaw this and realized that its adoption for naval ships, and the idea with the ship is that you just kind of keep going. It's like an airplane. You're just flying along at a constant speed versus in your car, you gotta like idle your turbine? No. And it's like you don't idle your airplane, or you don't idle your coal-fired power plant. The thing just wants to keep spinning. Okay, Parsons foresaw this and realized that his adoption for naval ships would speed its acceptance in the world of merchant shipping. He also knew that the British Admiralty held a history of resisting all innovation. They had notoriously instead insisted on wooden hulls when others were already using iron and initially rejected steam engines. Parsons therefore decided on a demonstration and conducted a remarkable vessel. Here it is, the Turbinia, figure 619. 30 meters, 100 feet long, less than 3 meters wide, and less than 1 meter of draft. So it's just, it's like a turbine torpedo. She was driven by 3 turbines in triple compound arrangement, delivering a total of 1.7 megawatts, 2,300 horsepower to the screw propellers. Taken in secrecy to Crows, she roared out into the 1897 Jubilee Review of the Fleet at split head with Parsons at the controls and traveling, it is said, at the unheard of speed of 33 knots. So he's doing 40 miles an hour, which no ship apparently had ever done.
Well, it's not really a ship, it's more of a torpedo.
Yeah.
That's so skinny and long.
I know, yeah.
But what would that ship be used for? I mean, like, realistically.
Well, I don't know, spying. You go out and spy on the enemy, or delivering a bomb, or shoot, I don't know, crossing the English Channel in record time. If you want to get over, just transportation.
Plus, convince the English Parliament or whatever's in control to put a little more resources into building a larger version.
I can see a larger version, yeah.
This is just a pilot model for the most part.
With an original name too.
Yeah, and as it was stated, they refused innovation no matter what.
Yeah.
But if this is right in front of their face, and proof, then what's going to stop them then?
Brushing their teeth.
Yeah. Well, anyway, that's
bad teeth.
that's kind of I thought there was some scandal behind Parsons. There typically is, but anyway, it's not as crazy as I thought. But anyway, there he is, sort of making history. All right, let's take a little break.